At the very heart of the controlled environment HVAC design are the air filters, and it would help both designers as well as users if we were to understand a little better how these filters actually work, so that we can derive the maximum advantage from this important element and an important investment. The first confusing thing about air filters is their nomenclature. The same item is referred to under so many different names. So just let's have a look as to where all the confusion can come from in terms of identifying the type of filter we refer to. Sometimes it's named by the way it works, the type of filter. It could be a mechanical filter, electrostatic filter, a chemical filter. Sometimes it is identified by the medium it is made of. Microfiberglass filters, glass wool filters, sintered glass filters, charcoal filters, dry fabric filters, oil wetted fabric filters, PU foam filters, membrane filters, silica filters, and lithium chloride filters. Sometimes it is on the basis of its execution. How is it made? So they say flange filter, a cassette filter, a box filter, a sandwich filter, a disc filter, a pleated filter, a mini pleated filter, separatorless filter. And sometimes what is its purpose? What is the application? So then they say pre-filter, coarse filter, final filter, fine filter, intermediate filter. To make things even more interesting, where is it fitted? The location. So a bank filter, or a terminal filter, or a ceiling filter, or a fresh air filter, or an exhaust filter. Sometimes they are by the function they perform or the acronym for it. For example, depth filters, fire retardant filters, fire resistant filters, HEPA filters, high efficiency particulate arrestor, ULPA filters, ultra low level particle arresters. Sometimes by the brand of the filter, the make, Flanders filters, Cambridge filters, Fox filters, Micro-V filters, Absolute filters. And finally, sometimes by their grade, type A or type B or type C or type D, grade 1, grade 2. Now whenever we refer to filters and we refer to their efficiency sometimes, it's always important to link them to the standard or the test method that is used, because different test methods may not always give you the same results. So here we have an example. You have EU classifications, you have ASHRAE classifications, you have CEN classifications, PC classifications, just around each one of them calling them different names. EN 779 refers to one range of filters generally considered to be pre-filters, and EN 1822 refers to those filters which we understand as either HEPA or ULPA filters. Now if we were to go by Eurovent, it goes on from EU1 to EU9. EU1 to EU4 are coarse filters, pre-filters, and EU5 to EU9 are slightly better pre-filters. CEN refers to the European normalization, and they call it under EN 779 G1 to G4. EU5 to EU9 are referred to as F5 to F9. The G filters are gravimetric, the F filters are opacimetric. That's the test method. EU10 to EU14 refer to the better HEPA filters, and EU15 to EU17 refer to the ULPA filters. The degree to which air is filtered plays an important role in the prevention of contamination and the control of cross-contamination. The type of filters required for different applications depends on the quality of the ambient air and the return air where applicable, and also on the air change rates. The table below gives the recommended filtration levels for different levels of protection in a pharmaceutical facility. Manufacturers should determine and prove the appropriate use of filters. In selecting filters, the manufacturer should have considered other factors such as particularly contaminated ambient conditions, local regulations, and specific product requirements. Good pre-filtration always extends the life of the more expensive filters downstream. The level of protection and air cleanliness for different areas should be determined according to the product being manufactured, the process being used, and the product's susceptibility to degradation. ISPE, in their baseline guide, had referred to a strategy where they said that the level of vulnerability of a process to contamination or cross-contamination will determine the level of protection that should be designed and given. So, if the risk of contamination to the product or process is low, then he refers to that as level 1 strategy. Why is it low? It is because the product or process is not exposed either to environment or to the operators. For example, it's closed. It is material in a closed pipe or a closed vessel and not exposed. And the human being does not interact with it. So the level of the risk of contamination is low. The next level 2, he refers to that as a protected environment or protection strategy. And here it is a situation where the product or process may be at moderate risk to contamination, because for a brief period in the process is either exposed to the environment or to the operator or to both. But brief period, not extended period. And finally, level 3 is where the entire process is vulnerable for contamination because it is totally exposed either to the environment or to the operator or to both. So in this table, the recommendations are: if it is level 1, it's a general area with normal housekeeping and maintenance like a warehouse or secondary packing. And EN779 G4 level filters, primary filters, are adequate. Level 2, a protected area in which steps are taken to protect the exposed pharmaceutical starting material or product from contamination or degradation, example manufacturing, primary packing, dispensing, etc. The production facility operation on 100% fresh air, primary plus secondary filters, EN779 G4 plus the F8 filters. When it comes to level 3, it's a controlled area in which specific environmental conditions are defined, controlled and monitored to prevent contamination or degradation of the pharmaceutical starting material or product. Production facility operating on recirculated plus ambient air, where potential for cross-contamination does exist. Primary plus secondary plus tertiary filters are required, example EN779 G4 plus F8 plus EN1822 up to H13 filters. EN779 relates to filter classes G1 to F9 as we have seen earlier, and EN1822 relates to filter classes H10 to U17. Now let us examine how HEPA filters are actually made. You have a conveyor belt on which there is a resin, and then you have the medium. It could be microfiber glass or it could be any other material. I will discuss the more common microfiber glass kind of construction. So you have very fine, it's like candy, budi kabal as they call it. So there it is, it will cut your fingers, it will cut your skin. So they wear gloves, of course. And they sprinkle it across. And then one more layer of resin, and then one more sprinkling of the microfiber glass strands. And then again a resin. And so they have as many as 3,000 to 4,000 such layers. And the whole thing then is sent to a roller which compresses it to 0.38 millimeters. And then goes across to a tunnel where it is baked and then rolled in sheet form. This is how it is made. Now let's look at some of its characteristics. High efficiency particulate air filter or arrestor, very fine glass fiber filaments, 1 to 100 microns diameter, 0.2 to 40 mm long, formed into a thin pad, 0.38 caliper, held in place by resin bonding agents, and the interstitial space is 1 to 10 microns, and the effective web depth could be 200 to 400 microns. Now when a HEPA filter is made in the form in which you use it, this sheet is pleated. And the reason why it is pleated is, the more the pleats, the more is the surface area of the medium. Now it could be pleated into 6-inch or 12-inch or whatever is the depth that you want. And in some designs, to see that these pleats don't collapse over one another, in other words, blinding does not occur, you have separators. Separators do two functions. One is to see that the media remains exposed and don't collapse over one another, and the other is to give the entire pleats some level of stability. And the entire thing is then put into a frame, glued in place, potted, and then sent to you. Now we have ULPA filters, ultra low level particulate arresters or ultra low level particulate air filters, whichever way you like to call it. Now they don't feature microfiber glass because in the semiconductor industry, as it advanced, it reached a stage where contaminant could come from anywhere. Microfiber glass is borosilicate. Boron is a semiconductor process material. Silicon is a semiconductor process material. So they did not want any process materials to be in the environment. They would rather that they add to the process, not that these come from somewhere else over which they have no control. So they were looking for a replacement for microfiber glass, and the answer comes in the form of Teflon because it is an inert material. So ULPA filters refer to a medium which is basically PTFE, which is expanded PTFE, a membrane-like thing which is expanded and then made into, assembled as a filter and made available. One important characterizing feature is called the MPPS, the maximum penetrating particle size. In the case of a HEPA, it happens to be 0.3 micron. In the case of an ULPA, it is 0.12 micron. Now, what is the significance of this? Or what does it really mean? We shall discuss now. For example, a HEPA filter. Most people refer to it as a 0.3 micron filter. As I said, 0.3 microns is the MPPS for a HEPA filter. Now, what does it really mean? Does it mean that a HEPA medium is like a sieve where anything that is smaller than 0.3 microns and up to 0.3 microns will go through, and anything that is larger than 0.3 micron will automatically be arrested? Is that what it means? Now let's see. Let me try to explain how the HEPA works, which is more or less the same way ULPA works, or any of your pre-filters work, or for that matter your membrane filter works. You see, when you have in college, when you were doing filtration, you took a filter paper and then you folded it, and then you folded it again, and then you folded it again. Why did you do that? To improve the filtration efficiency. Why? So that the pores do not align. The pores in the filter paper do not align. In a HEPA filter, because you have one layer of resin with the filaments thrown in, and then another layer of resin, and again at random thrown in, and again at random thrown in, the path through the HEPA filter for the air stream is not straight. In other words, if you have a filter paper thickness of 0.38 mm, the air path is not 0.38 mm. It zigzags inside. Suddenly you have, as I said, the interstitial spaces in a HEPA filter varies from 1 micron to 10 microns, not 0.3 microns, 1 micron to 10 microns. That is the interstitial space between the filaments. So air goes through, and suddenly you find that the path narrows down to 1 micron and then suddenly expands to 10 microns. And the path is not straight, the path is convoluted. It's like climbing up a hill station and motoring along a series of hairpin bends. So now let's say we have a situation where we have a hairpin bend and the vehicles are traveling along the road. For our discussions, we will consider 3 categories of vehicles. One, which is a SUV. One, which is a 10-ton truck. And one, which is a 2-wheeler. Now, the cautionary signal indicates that the best or the optimal speed for negotiating that hairpin bend is 20 kilometers per hour. If any vehicle, be it a 2-wheeler or a SUV or a truck, were to travel at 20 kilometers per hour, it could be reasonably sure of negotiating the hairpin bend safely and effectively. Now let us say for the SUV, the energy required, the torque required to maintain 20 kilometers per hour over that particular bend is this much energy. And for the 2-wheeler to maintain 20 kilometers per hour, the torque or the energy required is this much. And for the truck to maintain 20 kilometers per hour, it requires this much energy. Now, if we were to give the same torque, same energy to all 3 vehicles, and we have a person called Tom at the base, at the start of the hairpin bend. We have a person called Dick at the hairpin bend where the curve takes place. And we have a person called Harry at the end of the hairpin bend, way up on the hill. And we see that all three categories of vehicles are given the same energy. If Tom sees an SUV and he reports, here is an SUV attempting the climb, you can be sure it will travel with the correct amount of energy at 20 kilometers per hour. And therefore, you can see that Dick is also able to acknowledge that the SUV is coming through. And finally, when it negotiates the hairpin bend and goes up, you can see Harry also confirming that he can see the SUV passing. But if you have this much energy given to a two-wheeler, which really requires only this much for 20 kilometers per hour, at this level of energy, the motorcycle is traveling at 100 kilometers per hour. At 100 kilometers per hour, as he attempts the climb, Tom can certainly see him. But at that speed, he is quite unable to take the bend, and therefore Dick is able to see him just fly off the cliff into wherever. Harry is never going to see that motorcycle. Now, when a truck requires this much energy and you're giving it only this much, the truck, Tom can see it struggling to climb, but neither Dick nor Harry can ever see it because it simply doesn't have the energy to negotiate that hairpin bend. This is exactly what happens in a HEPA filter, ULPA filter, or any membrane filter. The path being so convoluted and the energy given to all airborne particles, be they 0.1 micron or 0.2 micron or 0.3 micron or 5 micron or 0.5 micron or 1 micron or whatever, all airborne particles are traveling with the same energy or delta P, as you might call it. So the airstream is moving at a certain velocity determined by the delta P or the energy given. At that energy level or velocity level, 0.3 micron is the one that is able to negotiate most of these bends and come out. 0.1 micron tends to go out of control and lost in the maze, doesn't ever come out. And the larger particles find the energy too low to be able to negotiate this convoluted path, and so they get arrested. So effectively, the one particle size that is able to, not that they all come out, no, they too get arrested. But if you were to see the profile of the particles coming out downstream, you will find the large majority of them belong to the 0.3 micron range, and the others are almost not there. This is how a HEPA filter works. And that is why the maximum penetrating particle size for a HEPA filter is 0.3 micron. Likewise, for an ULPA, the particle size at that velocity, at the rated airflow. Now, the rated airflow varies from filter to filter. But if the manufacturer says at 1 inch pressure drop, this filter will deliver 1000 CFM, then you know what the air velocities are. And at that velocity, for a HEPA filter, it is the 0.3 micron that stands the best chance of making it through, and particle sizes higher or lower tend to get filtered out or arrested. So what can we learn from this? How can we apply this intelligently? If now, instead of this much energy all vehicles are given only this much energy. Now, Tom sees the two-wheeler going up. Dick sees the two-wheeler successfully negotiating the bend, and Harry sees the two-wheeler passing by safely. But the SUV, which required this much energy, is now only given this much energy, finds it difficult to make the climb. And the truck certainly cannot make the climb. So what does this mean? If you were to reduce the air flow through a HEPA filter which is capable, rated capacity is 1000 CFM, you decide to pass only 500 CFM. In other words, instead of placing the HEPA filter at 1 inch pressure drop, you now give a delta P of only 0.5 inches, so that only 500 CFM comes out. Then even the 0.3 micron now finds it very difficult to come out, and a smaller particle size, perhaps 0.15 or 0.1 micron, is now able to negotiate those convoluted paths and come out in larger numbers, and all others are held back. What have you done? You have reduced the energy, and you have made a HEPA filter behave like an ULPA filter. You have paid for a HEPA filter, but you get the performance of an ULPA filter, and all you did was reduce the airflow through the HEPA filter. So if you need 1000 CFM, you have 2 HEPA filters instead of 1, and the airflow through each HEPA filter is restricted to 500 CFM. On the other hand, if you were to give this much energy to all vehicles, the two-wheeler goes out of control, the SUV goes out of control, and it is only the truck that is able to negotiate the hairpin bend and come out safely. So you have a situation where Tom, Dick and Harry, all three see the truck go through safely, but Tom sees the SUV pass by, the two-wheeler pass by, and Dick sees both of them going over the cliff. In other words, in a HEPA filter, if instead of 1 inch pressure drop, you were to give 1.5 inch pressure drop, you will have 1500 CFM of air perhaps passing through, more air coming through. But the particle downsides, the MPPs on the downstream side, will no longer be 0.3 micron, it could be 0.5 micron, it could be 0.7 micron, because now you have energized the heavier particles and empowered them to negotiate the convoluted path. So what advantages are there if you were to reduce the delta P across a filter from 1 inch to ½ inch? Since you need only ½ inch delta P, the booster blower can be much smaller. And please remember that this relates as a square. In other words, if you reduce the delta P by half, the energy consumption at the blower is down by 1/4. Because the energy requirement is 1/4, the speeds can be lower, there's much less vibration, there's much less noise, there's much less wear and tear, and the extra investment you made in that additional HEPA filter will be recovered with the energy and maintenance savings that you have within a period of perhaps even 1 year. And you now have downstream an ultra pure environment, an order of magnitude purer than the HEPA filter was originally designed for. This is the advantage of understanding a HEPA filter, how it works, and using it intelligently. Yet another interesting point to discuss about HEPA filters or ULPA filters or any filter is their efficiency statement. Now let's look at a HEPA filter, and let us say it is 99.97% efficient against a mono-dispersed aerosol of 0.3 micron or larger. If it is a monodisperse, it is 0.3 micron. If it is just any aerosol, 0.3 micron or larger. 99.97% is the efficiency. What does this mean? Let's look at it. 99.97 efficiency translates to 0.03% by way of penetration. 0.03% penetration means successful penetration through the media of 3 particles of 0.3 microns out of a total of 10,000 particles of 0.3 microns upstream of the media. In other words, number of particles upstream of the filter is 10,000, then the number of particles downstream is 3. But if it is 100,000, the number of particles downstream is 30. If it is 300,000, then you have downstream is 90. If you have 3,33,333 particles upstream, you land up with approximately 100 particles downstream of the filter. In other words, class 100 conditions cannot be attained by a perfectly normal filter if the upstream air quality exceeds or is worse than 3,33,333. For example, if there are 1 million particles upstream, for no fault of its own, the HEPA filter will release 300 particles, 0.3 microns or larger, on the downstream side. 333,333 is the theoretical upper limit of air quality upstream of a HEPA filter if it is to deliver class 100 or better air quality downstream. In practice, upstream air quality should be targeted to be better than class 100,000 if the HEPA is to reliably deliver air of acceptable cleanliness into the clean room. Similar limits for upstream air quality exist for other grades of depth filters, whether it is G1 or it is U17, if they are to be relied upon to deliver acceptable incoming air quality. So, what have we learned about HEPA filters? 2 important things. 1, that if instead of allowing the rated airflow capacity, that is, if it is 1000 CFM at a pressure drop of 1 inch, we were to allow less air, reduce the air quantity, the requirement in terms of the pressure drop required comes down. So you can use a smaller blower. The energy consumption drops dramatically. The noise and vibration comes down. Maintenance costs come down. And on the downstream side, the air quality goes up tremendously. That's one thing. The next thing is that if a HEPA filter were to qualify as giving first air quality of class 100 or better, the upstream air quality should not be worse than 333,333. In other words, if upstream you limit the contaminant density to less than 1 lakh, in other words, 30 particles of 0.5 microns or larger per cubic foot. And that's what you should aspire for. Now, is there anything else we can learn about HEPA filters? A HEPA filter, as it is put to use, gathers dust and dirt on its upstream side. It's a fine spray. If you look at any discarded HEPA filter, look at it, examine its upstream side, you will see that it's got a fine coating, a blackish, greyish coating. Now this build-up of dirt acts as a pre-filter. Any suspended particle upstream has to first negotiate the dirt layer before it can meet the media and then try to navigate through the convoluted path in the media. In other words, as the dirt builds up, the pressure drop across the HEPA filter does go up, but the quality of air that's coming out becomes even better and better, because now you have an additional layer serving as an additional filter. So what does this mean? On the day you discard your HEPA filter, it is functioning at its highest efficiency. This is one product which you invest on for a certain purpose, and that is good filtration, good efficiency in filtration. And when it is doing its job best, that's the day you discard it. Strange, isn't it? Now, some more information about HEPA filters. The air coming out of a HEPA filter may be at 100 feet per minute in a laminar flow unit, or if it's a terminal filter and it's a filter which is, say, 2 feet by 2 feet and the capacity is 1000 CFM, the incoming air velocity downstream is approximately around 240, 250. But if you were to see what is the velocity with which the air stream moves through the media, it's generally between 5 to 10 feet per minute. But in use, as you use it, as the manufacturer has asked you to use it, the air stream through the media is generally between 1 to 5 feet per minute. So, if you have a pleat, whatever be the height and whatever be the depth, one pleat would mean once in this direction, once in that direction, therefore you have two sides to the pleat. So you know the surface area of each pleat. Now you count the number of pleats. The media area per pleat multiplied by the number of pleats and multiplied by 5 feet per minute, assuming that is the velocity of the airstream through the media. This gives you what is called the actual rated capacity of that filter. Why I'm mentioning this to you is the depth as you see it outside could be 6 inches or 12 inches or whatever. But the manufacturer could compromise on the total media that you need or you're paying for by using a part of the rear and part of the front, filling it up with glue. So the effective pleat depth may not be 12 inches or 6 inches. It could be 10 inches, 5 inches, 4.5 inches or 5.5 inches, whatever. You measure the actual pleat depth and then you measure per pleat what is the surface area. And then count the number of pleats, because you normally in your specifications say we want filters 2 feet by 2 feet by 12 inches, so many numbers. It never occurs to you to specify the number of pleats and the total media surface area, and what you're paying for is for that media. So make sure that you get your money's worth. Now, what else can we learn about the HEPA filter? Now, let us see pressure drop across a filter is influenced by what? Now, the pressure drop varies directly with the media thickness. That means the air pathway increases as the media thickens. Therefore, the efficiency of filtration goes up, but the energy required to drive the airstream through the media also goes up. Therefore, the delta P goes up. As dirt builds up on a filter, the delta P goes up. And as you want more and more airflow through a filter, you have to drive it that much harder, that much more energy is required, therefore delta P goes up. Now delta P varies inversely with the pleat depth. The greater the pleat depth, automatically the media area increases per pleat, and therefore more surface area is available, more pathways are available, more air can come through with less energy. Now the pleat density. The more pleats you have, automatically the surface area of the media goes up, and therefore more pores of air pathways are available for air to move, and therefore the energy required is much less. Delta P would drop dramatically if there's any leak, because now air, instead of passing through the media, is now bypassing it and coming out. If the media is ruptured somewhere, then naturally your delta P will come down. Now it's alright to say that the more pleats you have, the more media area is available, and therefore more air is likely to come through for the same energy given to the airflow. A point may come when one pleat starts interfering with the next pleat, called blinding, and then the whole purpose is lost. Therefore, there is for every filter a certain optimal number of pleats at which it gives its best performance in terms of the airflow volume vis-a-vis delta P, or the energy required to deliver that much air. Now you have some filters which feature separators, and you have another design called mini pleat where you do not have separators. Now what are the advantages? Why do you have a separator to start with? As I mentioned earlier, to prevent blinding, to ensure that the media surface area is available for airflow and is not fouled. Secondly, it also gives a certain amount of rigidity. Now what are the drawbacks? Now this pleat could be aluminium foil or it could be any polymeric foil, but it's a surface. And the air passing through, if it is a supply filter, is usually at 18 degrees centigrade. The room temperature may be 22, but the air that is coming in is at a much lower temperature, usually 18. At 18 degrees centigrade, and the RH is not zero, RH is very much in the range. It could be 55%, it could be in a controlled environment where humidity is to be kept low, it could be as low as 25%, but it is still there. On a cold surface, the moisture naturally tends to condense. And once you have moisture, you have problems, because you could have a breeding ground for microorganisms. So constant fumigation would be required, but regardless, if the pleat is facing downstream and it is collecting moisture over a period of time, you could have biofouling. Secondly, if it is aluminium, you could have aluminium oxide being released into the room. Thirdly, with the aerodynamic vibration caused on each pleat filter separator, each separator vibrates and could either rupture the media over a period of time or compromise the adhesives on either end, leading to leakages. These problems are avoided in a mini pleat filter, a separatorless filter. Yet another concern is about pinholes or slight rupture that you can see in a HEPA filter. Question is, what do you do about it? Now, even if you were to say it's a brand new filter and you see something and the filter manufacturer says fine, and then he cuts a piece of the media from his bag, applies a glue and sticks it, like as if he's putting a band-aid, would you allow it? The answer is, the standard that governs HEPA filter manufacture permits within reasonable limits. And what are those limits? Let's see. Patching of HEPAs is permitted by the standard, provided each patch is less than 2 square inches per spot, and the totality of such patches is less than 3% of the total filter face area. Filter face area means if the filter size is 2 feet by 2 feet, the filter face area amounts to 4 square feet. And any patch shall be less than 1.5 inches long. Please remember, every time you patch something with glue, that becomes a dead spot. There is no more air flow through that spot. It's a dead spot. Yet another point to bear in mind is, when you wish to replace HEPA filters, you don't replace them one at a time. If they are terminal filters, you might replace 5 of them at a time, or 10 of them at a time, or whatever. And it is not like just-in-time inventory. You have to plan a shutdown, and therefore on the day it is shut down, the filters should be available. So you wouldn't like to announce a shutdown and then wait that morning for the filters to arrive. So you plan ahead. The filters arrive earlier. Question is, how do you store them? Where do you store them? What care should you take? It should be stored not on the ground, but on some kind of a rack. And it should be stored vertically, not horizontally. And you should never have one HEPA filter resting on another HEPA filter. They should be kept aside, separate racks, each rack holding a series of HEPA filters side by side, but not one on top of the other. And the place should be like any other place, dry, no wet spots anywhere, and under normal ambient conditions. When do you have to replace a HEPA filter? This is a question very many people ask. And most manufacturers answer that if on the day it was installed, it had a certain value, delta P, when that delta P doubles, that's the time to replace it. For example, on the day you install it and measure the delta P and it is 20 mm of water, then when it reaches a level where the delta P reaches 40 mm, that's when you replace it. But this is a very crude way of deciding when to replace a HEPA filter. Because a HEPA filter manufacturer, as per the standard that he follows, is expected to test his HEPA filter's integrity by subjecting it to a pressure of 10 inches of water, not 1 inch, 10 inches of water. Now the filter should remain stable for at least 1 hour before anything happens to it. A minimum of 1 hour at 10 inches of water pressure. Now, those who are in radiopharmaceuticals or in biologicals are not allowed to remix contaminated air. So it is a one-pass system. They have HEPA filters on the supply side and they have HEPA filters on the exhaust side. And if they were to follow this rule, they would go bankrupt replacing filters. So many of them design their AHU in such a way that it can go up to 6 inches of water pressure. So if on the day it was installed, it was 20 mm, they can wait until it reaches 150 mm before they replace. If you are able to design your HVAC system in such a way that it can deliver additional delta P as and when required, then you need not replace the filter when the delta P doubles. It can go on. Strictly speaking, in any clean room featuring HEPA filters or ULPA filters, if the upstream air quality is maintained at 1 lakh or better, you seldom have to ever replace a HEPA filter. There are facilities all over the world where filters have not been replaced for 15 years. So there is no reason why you should be replacing your filters every 2 months or every 2 years or every year or whatever. That's as far as replacement of filters is concerned. Now, how good a HEPA filter is in its function would depend tremendously, not just on the way it is assembled, but also on the way in which it is mounted. And that's an area of great concern, because most people have not quite paid the amount of attention that a mounting, the frame that holds the HEPA filter, should be designed. Now, if you were to have a gasket and the gasket rests on a flat surface, over a period of time, the gasket could harden, and then once it is hardened, the gasket could start permitting a leak. There are ever so many innovative designs. Now, in his book Cleanrooms, designed by Dr. Bill White, he has shown two very interesting designs for mounting frames. One featuring a knife edge if it is a gasketed filter, so that the knife edge protrudes into and presses against the gasket and effecting a very strong seal thereby. And another frame where there are filters that are potted in place, gel sealed. They don't have any gaskets, so that you don't have worries about particles coming into the room. So it is a gasketless HEPA filter which is potted in place using a special gel, and the frame for that has been shown by Dr. White in his book, which is reproduced here. Now, while we are still talking about mounting of HEPA filters, the way it is done now is such that if the fitting is improper or if the gasket is leaking, then air upstream bypasses the HEPA filter and enters or invades your facility, placing at risk your product or process. Now, there is an innovative design in which all supply ducts, from the time it reaches the HEPA filter and back, is enveloped with a return duct connected to the air handling unit. In other words, the HEPA filter is surrounded by a zone of negative pressure. Now, if there is any leak in the gasket or in the fitting or in the mounting, air from the room is sucked back by the return negative pressure zone surrounding the HEPA filter and taken back to the air handling unit. Air is sucked back into this negative pressure zone surrounding the HEPA filter and returned. So you do not have any risk of contamination if there should be any leak in the gasket or in the fitting. This is an innovative concept, and you're encouraged to try it in your next design. In biologicals, the HEPA filters, ULPA filters, and just around any filter, normally you have a once-through system. You seldom recycle air in biological facilities. It's a one pass. So those filters that have been exposed to the organisms, the pathogens, are infected. And when you choose to change such filters, you must first follow very strict biosafe protocols for decontaminating these filters before anybody handles them. Here we have an arrangement where we have a filter which can be removed safely using a concept or technique called bag in, bag out filters. So effectively, the filter is pushed into a bag and sealed without having the operator to physically touch the infected parts of the HEPA filter. Is there anything more we can learn about air filtration to improve the quality of the air? Yes. We have so far talked about mechanical filters. HEPA filter, ULPA filter, these are all mechanical filters. You can have an electrostatic precipitator, which was in use before the HEPA filters became popular and replaced them. But most people abused the electrostatic precipitator rather than using them intelligently. The problem with electrostatic precipitators is that they chatter, and they constantly arc, and while you have plates that collect the dirt because of constant vibration, sometimes over a period of time the layer that has been accumulated on a plate could break loose and then come downstream and contaminate the environment. These are some of the many concerns. Now, yet another thing is because of the high voltage. If you were to have any environment where there are vapors and solvents, and which could lead to an explosion or fire, then it is contraindicated. But if your environment permits, there is no danger of explosion, and your environment permits the use of an electrostatic precipitator, you could place it upstream of the HEPA filter, never downstream, not in the clean room, but in the air handling unit or the plant room, where the air passes through after its pre-filtration. It passes through the electrostatic precipitator before coming into the supply duct and then getting filtered down by a HEPA filter. Now, what are the advantages? The electrostatic precipitator first and foremost removes static charges from the air. Now, in what way does that help you? If ever you have a suspended particle, very, very small, and it carries a charge, the two particles of opposite charges could then form and coalesce and become a larger particle. When they came through the filter, they were small, but they carried the charge. But later, they could meet and coalesce, and over a period of time, they could come down as a much larger particle and contaminate your workplace. Yet another danger is, whenever there is a charged particle, it wants to drain its charge. And therefore, if it sees any surface on which it can drain its charge, any metallic surface, it is like ground for that particular charge. So it darts down and releases its charge. So a statically charged environment is an environment where contamination risks grow. And once you have removed the static charge, then you have reduced this particular risk. What other advantages? The air in the room, over a period of time, if you start at 8 in the morning, by around 3 o'clock in the evening, you can start feeling the fatigue. You can get that smell, that odor, that staleness that is there in the air. An electrostatic precipitator freshens the air. It removes odors, it removes vapors, smoke, and whatever else have you, and rejuvenates the air so that it smells as fresh at the end of the day as it was at the start of the day. Lastly, an electrostatic precipitator absolutely blows away any microorganism that comes in its way and any virus that might come in its way. It just incinerates them. That's about it. It generates ozone, and that radical oxygen is enough to clear out all the odors, all the smoke, and all microorganisms that come in its way. So, the right place to use an electrostatic precipitator would be upstream of a HEPA filter, so that if anything comes loose from the electrostatic precipitator, it is arrested by the HEPA filter. And if the electrostatic precipitator were to function as intended, you must have an SOP that requires cleaning off those plates, collector plates, on a regular basis. It could be once a week, it could be more frequent, it could be less frequent. It depends on the environment in which it is placed and the dust load in that place. There is another model that somebody has come up with where he has called an electrically enhanced HEPA filter. So in other words, upstream of the HEPA filter, he gives two meshes. One mesh, and the meshes are not in touch with each other. One mesh which is highly charged, and the other mesh which is grounded, and therefore it acts like an electrostatic precipitator. Now, if you see the HEPA filter without any such electrostatic assistance upstream, whether in terms of an electrostatic precipitator or this mesh arrangement that I spoke about, you will find that the quality of air coming downstream goes up by an order of magnitude. The maximum penetrating particle size may continue to be 0.3 microns if it is at rated airflow, but you will find the total number of such particles coming out is reduced by an order of magnitude. So you have very high air quality, very clean, very fresh air coming out if you use this technique. Now, is there anything else we can do? Now, all of us use silicon gel for humidity, lithium chloride in a more controlled way when your humidity has to be controlled more precisely. It's a chemical filter. Now, there is one more thing you can do. Use activated carbon granules. Now, you put them into a muslin quilt. You see, you just sort of make little pockets in which these granules are and just suspend them in the plant room, in the air handling unit area, so that the air passes through this before it gets into the supply duct. You will find vapors are removed, odors are removed, because 1 cc of activated carbon can absorb 1000 cc of gas. Now, a chemical filter will perform perfectly and suddenly it loses its filtration capacity, absorption capacity. On that day, you just have to take this out and sun it on the roof. It regenerates itself automatically. So if you have an SOP of using these quilts filled with carbon granules, and then you say every week it shall be sunned for a period of 4 hours or 8 hours or as need be, you have an excellent air quality assured in your clean room. This is an example of a HEPA filter which has got the electronic air filter grid upstream, and upstream of that is a bed of activated charcoal granular bed, and the air comes through a filter, pre-filter, goes through a blower and then goes through these banks, first activated charcoal and then the electric field and then the terminal HEPA or ULPA filter. The air comes through of a quality that will only delight you. And the filter's life, the HEPA filter's life, is extended by, again, a very, very substantial period. Well, so much for air filters. Now let's talk about diffusers. Downstream of a HEPA filter, the manufacturer or the designer has normally given you a diffuser. Now the diffuser could serve very many purposes. First and foremost, it protects the HEPA filter from accidental damage. The gap between the HEPA filter and the diffuser could serve as a plenum. In most of your laminar airflow units, you'll find that it serves the function of a plenum so that the air is distributed and the velocities comes through more uniformly. Now in the terminal filter, you have different types of diffusers. Which diffuser is right and which diffuser is wrong? Let's have a look. Supply air diffusers of the high induction type, example those typically used for office type air conditioning, should where possible not be used in clean areas where dust is liberated. Air diffusers should be of the non-induction type, introducing air with the least amount of induction so as to maximize the flushing effect. Now, what is the meaning of this induction? If you have a HEPA filter all by itself, now you have air coming through it at a certain velocity, let's say 250 feet per minute in a terminal filter. Now, in that area where the HEPA filter is, you have high velocity, but around this ceiling, around the HEPA filter, there is no airflow. So whatever dust may be hanging there, suspended, gets sucked in because of the Bernoulli-Venturi effect. And because this is a low pressure area, it gets darted in. So it just draws any suspended contaminant around the HEPA filter and the air streams that are coming down high velocity induce around the flow area, whatever may be suspended is drawn in and thrown on to your product. So this is to be avoided. Now, why do they use diffusers apart from protecting the filter? The general, or let's say, the principal purpose is because for the HVAC engineer, he wants uniformity of temperature and uniformity of humidity throughout the room, no matter where it is measured. It should be within an acceptable tolerance or window. So he tends to diffuse the air in such a way that the cold air mixes with the hot air and you have a reasonable parametric profile that is maintained. You have non-inducing or reduced inducing type of diffusers as well. One is shown here as a perforated plate diffuser, and the other is referred to as a swirl diffuser, both of which tend to discourage induction. But as I said, for the separator, the diffuser may be metallic or polymeric, but it is a surface and it is encountering air at 18 degrees centigrade with moisture in it. That renders the entire diffuser surface very cold, and therefore condensation does take place, moisture buildup takes place, then microbial buildup will naturally follow eventually. Therefore, if ever you use diffusers, you must have an SOP for removing the diffusers, sanitizing the diffusers periodically and putting them back. Otherwise, you might find unexplainable biocontamination in your